Hey everybody, how's it going? My name is Cameron Dennis. I'm the president and founder of the Blockchain Acceleration Foundation. Um, Lai Wen, I'm actually making you a speaker right now if you want to come up. And this is Eli Jaffe. He will be giving the lecture today about the introduction to zero knowledge proofs. But hey, how's it going, Lai? Hey, Lai, can you hear us?
Yeah,
Test.
sorry. I had
Amazing.
a bit of a disconnection. Yeah.
Great. So it's good to be here. Thank you everyone for coming. Lai Wen, do you want to introduce, I guess, the club and I guess what we're doing today?
All right. So so we are today we are talking about zero knowledge proof. So Cameron has kindly taken his time off his schedule to get Ally to talk to us about how is it Findora or is it now under PAF?
We'll be talking about some of the underlying principles that kind of serve as the infrastructure of Findora. But this is a collaborative effort between the Blockchain Acceleration Foundation, which is a nonprofit based here in the United States that starts accredited blockchain courses at universities, and we work with a bunch of different schools from around the country to teach people about Web3 and decentralized internet. And we also, Eli and I, collaborate with the Findora Foundation and talk a lot about zero knowledge proofs and whatnot. So yeah, that's about the background of the relationship. So yeah, I think we should probably just get started with Eli. And actually, Lai Wen, is there anything else that you'd like to mention about the club?
No, I think we covered it during our prior meeting, but we're all excited to be in this event today. Yeah, so thanks again for organizing this.
Absolutely. And if anyone else wants to get more connected to other blockchain protocols in the industry and meet a lot of the great researchers and students that run blockchain clubs in the United States, I'm going to drop our membership application here. And this is the way that we're actually, the whole goal is to create an automated and tax-exempt nonprofit where we get people opportunities in the space. This is in the form of jobs, internships, research opportunities, and we actually host weekly meetups. It's not the best time for everyone based in Singapore, but there is every Thursday we host a meetup. So this is the best place to kind of meet the community. So thank you, Lai Wen, for organizing, and I'm going to drop this link in the chat and quickly introduce Eli Jaffe. He is a PhD student at UCLA studying cryptography with a specialization in multi-party computation and zero knowledge proofs. So Eli, you can take it away. And Lai Wen, if we can just both turn off our mics and cameras, our screens will minimize.
All right. Thank you, Cameron, for that great introduction. Let me just quickly get my slides up and then we can start the presentation. Okay. So, like Cameron mentioned, I'm Eli Jaffe. I'm a PhD student at UCLA. I study cryptography with my advisors, Rafi Ostrovsky and Len Kleinrock. And I'm specializing in cryptocurrencies, zero knowledge, and multi-party computation. And I'm really excited to be here at the National University of Singapore, virtually, to talk to you guys about just that, cryptography, blockchains, and zero knowledge proofs. So, basically what we're going to learn today is the fundamentals from start to finish of how a blockchain works and how we can achieve privacy on a blockchain. So for those of you interested in doing finance over blockchains, this is going to be crucial information. So without further ado, let's go ahead and get started. I'm going to pause for questions at certain points throughout the presentation. So if you have a question, just go ahead and drop it in the chat, and I'll try to check back from time to time to get the questions. Let's start with the basics. Cryptography's basic question is, how can we use data without revealing it? A simple example, Alice has a message M, and she wants to send this message to Bob, but she doesn't want Eve, who's listening in on the transmission line, to learn the message M. One basic solution to this problem is for Alice and Bob to somehow agree upon a secret key, K. which is just a number. And now Alice, if her message, we also think of that as a number, she can take her message M and add it to her secret key K and send that as the ciphertext to Bob. And Bob can simply take that ciphertext, subtract the secret key K that he also knows, and extract the original message M. And Eve will have no idea what the message M was, because since she doesn't know K, M could be anything. Now, people have been doing encryption for a long time, pretty badly. One of the first schemes that people came up with was during ancient Roman times. Military generals would actually take their secret messages that they wanted to send to each other. They would shave their messenger's head. They would tattoo it onto the scalp, and then they would send the messenger to, their other general. And their assumption was that if the enemy doesn't know that this is how we're sending our messages, then they won't know how to find the message. I think all of us can agree that this is not a very good encryption scheme. It relies on the enemy not knowing how we're encrypting our message, and that's generally something we don't want to do in cryptography, so-called security by obscurity. You guys also might have heard of something called the Enigma machine. This was a famous encryption machine in World War II, used by the Germans, and it used a really complicated set of gears on the inside to decide a new key every day. But it had a crucial flaw, which was that it never mapped any letter to itself. So if my original letter in my original message was an E, then in my ciphertext, it's never going to still be an E. And that was one of the flaws that led to it finally being cracked by Alan Turing and his team, which eventually swung the tides of World War II. So both of these schemes face a sort of similar problem. They rely on some kind of claim of security, either based on the enemy not knowing what scheme we're using, or the enemy not being able to figure out that no letter ever goes to itself. And unfortunately, those assumptions are always eventually broken. So, ideally, we would like to build our cryptographic systems off of assumptions that won't be broken, or at least if they are broken, that means something much more important. So let's move into the modern day. What does modern cryptography look like? Well, like I just said, we have figured out better ways to prove our security. And in fact, what we do today is, if I want to prove that my protocol is hard to break, my protocol will inherit that hardness from some kind of old math problem, some kind of well-studied assumption in mathematics that people have been studying for a long time and people very much believe to be true. So some examples of this are the discrete log assumption, factoring assumption, learning with errors. These names might not mean much to you, but every single one comes down to some kind of statement that says there is not an efficient algorithm for doing blank, not an efficient algorithm for computing the discrete log in some kind of particular group, or for factoring large numbers if they're made up of two large coprimes. So all of these different mathematical assumptions are just things that mathematicians think are hard. And what do we do with these? Well, we say, if you can break my cryptographic protocol, then in fact what you've actually done is falsified one of these well-studied mathematical assumptions. So you broke my protocol, great. You just came up with a solution to the discrete log problem, which nobody's been able to do for the past 100 years. And so you may have broken my cryptographic protocol, but you probably also earned yourself a Fields Medal in the process. So, if you believe that it's hard to win a Fields Medal, you should believe that it's hard to break my encryption scheme. From these mathematical assumptions, we've been able to do a lot more than just encryption. So one of the first things that we built are so-called pseudorandom generators, or pseudorandom functions. And these are deterministic protocols that take a certain amount of true randomness, like a short, truly random string, and stretch them into a much longer string that looks random to anybody who might look at it. So this is really important because generating randomness is expensive. The machines in your computers that flip random bits, it takes a lot of work to actually flip a truly random bit. So by using these pseudorandom generators and pseudorandom functions, we can create things that seem random to anybody who might look at them, but in actuality, we didn't have to work so hard to get these random numbers. We can also encrypt things homomorphically, and what this means is that if I encrypt one number x and I get a ciphertext, and I encrypt another number y and I get another ciphertext, I can actually take these two ciphertexts and I can combine them together to get x times y or x plus y, in different ways. And so what this lets you do is take data that's hidden, encrypted, and perform functions on it. And we've been able to do a lot of really interesting stuff with different kinds of homomorphic encryption, especially outsourced computation. One of my favorite things to talk about is multi-party computation. So in a multi-party computation, what you have is a bunch of players who each have some private data, and together they want to compute a function on that data. So maybe we want to add together all of our secret numbers. Maybe we all have some amount of money in our bank account and we want to know who's the richest. But the crucial thing is that none of us are willing to reveal our data to the other person. So we all want to learn, the max or the min or the sum, but we shouldn't learn anything more than that. I shouldn't learn what your value is, and you shouldn't learn what my value is. And so this is an extremely general notion. You can do almost anything in a multi-party computation without revealing what you're doing. And so today, people are actually working not just to prove what you can do in multi-party computation, but actually do it efficiently. And people are coming out with really cool systems for efficiently computing some of these multi-party functionalities. A digital signature is something that is maybe a little bit easier to wrap our minds around. It's just like a real signature. I have a piece of data and I want to attach a little stamp to it such that nobody else can replicate my stamp. But if somebody looks at it, they can tell, oh yeah, this was stamped by Eli. This is a valid signature from Eli. And these digital signatures are very important for data authentication, which is crucial for blockchains and cryptocurrencies. So blockchains and cryptocurrencies, I should say a blockchain is an authenticated data structure where what you essentially have is a long list of transactions. And each set of transactions that gets added to the blockchain is approved in a distributed sense by the entire group of participants. And so instead of having one party who controls the entire database or ledger, you now have a group of participants who collectively add transactions, maintain the state of the blockchain, and use digital signatures to verify that they're acting correctly. And on top of a blockchain are built cryptocurrencies, and beyond that, lots of other kinds of decentralized applications. So before we get into too much more detail about blockchains, let's pause a little bit and take some questions about the basics of cryptography. So let me jump back to the event. Okay, doesn't look like we have any questions yet. Well, I have a sort of, general question. What makes you most passionate about blockchain and zero knowledge proofs? What makes me the most passionate about blockchain and zero knowledge proofs? These are kind of separate questions, so I'll start with blockchain. I really love the idea of self-governance, and I think that centralization is one of the biggest plagues to our society overall. It's a cause for abuse. It's a cause for just laziness and mismanagement. And when you distribute, democracy is one of the greatest things to happen to our society ever. And I see blockchain as bringing democracy to the technological space, because right now what we have is technologies that are autocratic and authoritarian in nature. You know, anybody can make decisions at any time about your service that you're using, and that's not really the way things should be. So I see blockchain as a way to move us towards a more democratic future in the space of technology. And zero knowledge proofs, one, just an amazing piece of mathematical trivia. Like the fact that you can even do something like this, in my mind, let alone doing it efficiently, is amazing. And what's even cooler to me is that it has this perfect fit within blockchain. And we're going to talk about this a little later, but zero knowledge proofs, you know, their perfect application is really blockchain. And so now we're getting to see all of this cool progression in terms of zero knowledge proofs because of how they're being used in blockchains. And I think that is a perfect segue for us to get back to the presentation and talk about blockchain fundamentals. So what is a blockchain? We're mostly going to talk about blockchains from a functional level, by which I mean we're going to talk about what they do and not sort of how you make them or what they are. And we're going to treat what they do as what they are. So what does a blockchain do? A blockchain is essentially a public, decentralized, append-only ledger. So let's dig into each of these terms. It's public in the sense that everything that's stored on the chain is available to all of its participants. It's decentralized in the sense that no one person is holding the data on the chain. Everybody's collectively maintaining it. And it's append only in the sense that you'll never remove any approved transaction from the blockchain. You can add a later transaction to sort of update the contents, but you can never actually remove that transaction. And it's called a blockchain basically because of this structure that it classically takes. You know, not all blockchains actually look like this, which is kind of funny, but we still call them blockchains. But basically the reason we call them is most blockchains look like a set of transactions arranged into a block with some kind of link between the blocks, which usually consists of a digital signature and a hash function. I'm not going to talk about too many details of this, but the hash function and the digital signature link all of these blocks together so that you can track the history of the blockchain back to its sort of genesis block right at the beginning. Okay, so that's what a blockchain is. Why do we care about this? Why is this useful? So kind of as I alluded to before, right now we use ledgers all the time, all over, in many different areas of business, especially finance, but we centralize them. So we put them in the hands of a particular company or a particular government agency, etc. And centralization like that leads to attack and it leads to abuse. So your data can be hacked if it's being held by a single person. Anybody can access it if they gain access to the third party who's controlling it. Even if they don't gain access through hacking, you know, the company holding your data might just decide to sell it. This happens a lot. And, you know, even if you're not worried about your data necessarily getting out, the people holding onto your data don't have any, you know, reason not to modify it if it's beneficial to them. You know, you have to trust whoever's storing your banking information that they're going to accurately store your information and they're going to tell you your correct account balance, and you don't have any opportunities to verify that information for yourself. So, you know, these are all of the problems of centralization. Blockchain essentially solves these problems by distributing the responsibility of protecting your data. Instead of putting it with one person, distributing it among all of the participants in the network. So what sort of data would belong on a blockchain? You know, I've laid out kind of how we can use it as a ledger, but it's not clear what you would use a ledger for. So basically, as I've described it, anything can go on a blockchain as long as it's allowed to be there permanently. So long as you never need to remove something from the blockchain, it's really able to store anything. In terms of what it's the most useful for, people have really found it useful for financial transaction records, personal identification information and credentials, details of contracts, which can be self-executing. These are so-called smart contracts, pieces of code that are stored on the blockchain. You can use a blockchain to store your medical history or your employment history, or even for voting, you can store votes on the blockchain so that all of the results of the election are publicly auditable. The only important property is that the data never needs to be removed from the record. So there's a key problem that I've been intentionally not mentioning until now, which is, what about privacy? So, I mean, without privacy, we're not really doing much, right? If we go back to these problems that I brought up with centralization, the first two bullet points deal with my data being given to people who I don't want it to be given to. So obviously, I want my data to be private in some sense. But, as I've described it so far, a blockchain is a totally public and decentralized system. Everything that's on the blockchain is available to everybody. So how am I going to use this for finance? How am I going to use this for medicine? How am I going to use this for voting? It's just not going to work. People won't be willing to do that. And in fact, even if we were able to make some things on the blockchain private and some things public, that's not really enough, because for things like finance, we often need to reveal this data to people like auditors, people who are making sure that our financial transactions obey the law. And in the case of medicine, we need to reveal our medicine history in some cases to our doctor in the right circumstances. And in the case of voting, it wouldn't be very helpful if votes stayed private forever. We need to keep the individual votes private, but reveal the sort of overall election result. And so all of these applications actually require selective revealing of the private data. So some kind of method to post private data to the blockchain, but also to verify some kind of properties about that private data. Now, normally, we're able to do that in the real world by relying on our centralized authority. So if Chase Bank is holding my financial transactions in their ledger, then, if they need to reveal my data to a third-party auditor like the IRS, they can just choose which data is important to reveal, and they can do it themselves. Now, obviously, this is bad for everything I just mentioned: abuse, hacking, etc., but also because we're introducing another level of trust here. I'm not the IRS. Everybody has their own level of trust in government agencies. I'm sure that I'm saying the IRS, but I'm sure that you have a comparable agency in Singapore that handles the tax services. But basically, I have to trust whoever's doing the auditing, and I don't actually get to verify for myself that my information is being handled correctly. One, idea that sort of sounds good on its nose is to use a so-called private blockchain. But in reality, a private blockchain doesn't give us any kind of selective privacy. It's just a normal blockchain where the set of users has to register themselves beforehand. And once you're on the blockchain, you can see everything on the chain just like normal. And so this kind of brings us to our question that we hope to answer with our presentation, which is, how can we actually get this privacy and auditability at the same time in a public decentralized system like a blockchain? And the answer to that question is going to bring us to our buzzword of the day, which is zero-knowledge proofs. And before we dive into the details of what that means, I'm going to pause one more time to take some questions. All right, I'll just wait, 10 or 15 seconds, and then I'll move on. Okay, let's get on to zero-knowledge proofs. So to begin, what is a zero-knowledge proof? Abbreviated ZK proof. Put simply, it's a protocol between two players, a prover and a verifier. The prover wants to convince the verifier that a particular statement X is true. And here, statement X is known to both the prover and the verifier. So for example, the prover might transfer some asset on the blockchain, and he might wish to prove to the verifier that that transaction was valid according to the rules of the asset transfer. At the end of the zero-knowledge proof, at the end of the protocol, the verifier should learn nothing except for the fact that the statement is true. So in the example I just gave, I, the verifier, will learn that your asset transfer was valid, but I shouldn't learn what asset you transferred, who it was transferred from, who it was transferred to, how much of the asset was transferred. None of these details should be revealed. This is the so-called zero-knowledge property, and this is why they're called zero-knowledge proofs. Zero knowledge, in addition to the fact that the statement is true, gets revealed by the protocol. So here's another simple example. Peggy wants to prove that a certain transaction doesn't cause her balance to go into the negative, and Victor wants her to prove it. And these zero-knowledge proofs, these protocols, usually come in the form of some kind of challenge and response game. So Victor will submit a random challenge, and Peggy will try to respond to that challenge. And the way that these challenges are set up, if Peggy's statement is true, then it should be easy for her to answer the challenge every time. But if her statement isn't true, then there should be some reasonable probability that she fails the challenge. You know, she might get lucky and succeed, but there should be a good chance that she fails. And so then what they do is they repeat this challenge response game over and over again with new random values. And if what I just said is true, if she has a significant chance of failing each time, if her statement is false, then she will eventually fail some challenge and Victor will say, no, your statement is not valid. But if she passes every challenge, then he'll say, okay, I'm convinced with extremely high probability that you are telling the truth. So you are telling the truth, or you got really lucky with these challenge response games. So that covers the basics of a zero-knowledge proof. One thing that you might hear a lot in the blockchain world is this idea of a non-interactive zero-knowledge proof, or a NIZK. So as I described them, most of these zero-knowledge proofs are interactive protocols, you know, a challenge-response game with multiple rounds. But some of them can actually be made non-interactive. And what I mean by non-interactive is instead of Peggy and Victor having to talk back and forth with each other, Peggy can just post her proof, and then Victor can come along later, read the proof, and check it for accuracy. So they don't have to talk back and forth. They don't even have to be online at the same time. And this is sort of more in line with our natural idea of a proof. You know, when I say proof, like in a math class, most people think something that you can write down, and then anybody can come along and verify it. You don't think of this sort of interactive game. This interactiveness is, you know, sounds more like an argument, more than a proof. And the crucial property that you get from these non-interactive zero-knowledge proofs is that the proof that you get is publicly verifiable. So what I mean by this is, in the interactive proof, if I wanted to convince multiple verifiers of a statement, I actually need to interact with every single verifier. But in a non-interactive zero-knowledge proof, I can broadcast this proof, you know, to all of the verifiers, and then they can just check it on their own. Every single one can check it in their own time, and we don't need to have all of this interaction. So here's a visualization of that. Peggy wants to prove that her transaction doesn't exceed her current balance. She creates her proof. She broadcasts it to the verifiers. And in their own time, the verifiers can learn that the statement is true. but they don't learn anything else. So just to put all the dots together, how can we use zero-knowledge proofs and non-interactive zero-knowledge proofs in blockchains? Well, it turns out the solution is we don't store our data directly on the blockchain, or at least our private data. Anything that we want to keep private, we don't store it directly on the blockchain. Instead, we create what's called a commitment to that data, which is basically just something that hides your data. It doesn't reveal what your data is, but it binds you to that particular value. Later on, you can reveal some extra bit of information that says, oh, this is actually the value that I committed to, and you can't change your mind with that process. Basically like taking your data, locking it in a virtual safe, and then later on opening up and saying, this was the data that I locked in the safe. Often people use a hash function for this. So what you can do is take your commitment to the data and construct a zero-knowledge proof that there is a piece of data that creates this commitment and which is valid. So just to ground that in a real-life example, if I'm trying to prove that my transaction is valid, I'll post a commitment to my transaction and then a proof that the thing that I used to make this commitment, the transaction that I used to make this commitment, is valid according to whatever rules are on the blockchain. Now, later on, if somebody needs to know something else about my transaction, if some kind of auditing agency wants to confirm some additional properties, like that my transaction was compliant according to some new law, well, then I can actually just post a new zero-knowledge proof, which corresponds to the same commitment. And so I don't have to, re-upload anything or redo anything. I can just give a new zero-knowledge proof. So again, here's a visualization of what that would look like. Here, instead of just being a broadcast channel, we're actually posting to a blockchain in a proposed block. And so Peggy would propose, some data on the blockchain, which says, I know an X, which is a valid transaction, and produces this commitment. And then she would post her commitment, H of X. And then she would post her zero-knowledge proof, which actually proves that statement. It proves that she knows the transaction X, that it's valid, and that it produces this commitment. And then each of the verifiers, once again, learn that the statement is true without learning anything about the transaction. So let's get back to some examples. This is all fine and dandy. We can post stuff on the blockchain privately, and we can prove properties about that stuff. But how does this affect the real world? Well, essentially, we can do all of the things that we were trying to do before. So remember, we wanted to do voting on the blockchain, but we need to count people's votes and reveal the result of the election without looking at everybody's vote. So now, instead of posting my vote directly to the blockchain, I post a commitment to my vote, and I post a zero-knowledge proof that says, hey, this vote was valid. And then later on, we can collect all of the votes and sort of sum them together and get the result. And similarly, if you have some kind of location-based reward system on blockchains, you can get location data without revealing it. You can receive medical data and authorize it for use by particular people without revealing it to everybody. We can even do outsourced computation with this. So imagine a company like Amazon or Tencent who has a lot of computing power, and you who have some private data, and you want to send some encryption of your data to the servers so that they can run some computations on it. Maybe I want them to run their fancy machine learning algorithm on my data set. So what we can do is we can hide my data, and that we can also hide whatever machine learning program they're running on the data, and yet they can give me back the result of the computation, which is pretty cool. And there's even been sort of more eclectic things like games that people have played on blockchains. You can post a move in the game to the blockchain without revealing to all of the other players, what my move was, so that you don't ruin your strategy and reveal it to everybody else. So you can, in a distant future world, you can imagine playing StarCraft and League of Legends all over the blockchain. Okay, so that is a crash course on zero-knowledge proofs and non-interactive zero-knowledge proofs. We're going to continue in a second with some more details on how you can evaluate zero-knowledge proofs and what kind of different forms they come in. But for now, we're going to pause a little bit and see if there's any questions. Awesome. So we've got some questions in the chat. How do you feel about big banks using blockchain? How do banks plan to expand using blockchain in the future? Doesn't it defeat the purpose of decentralization? This is a really good question. So I understand the sentiment. I personally wouldn't trust a big bank blockchain as much as I would trust a publicly run blockchain. But the cool thing about blockchain software is that it's totally open source. It's a decentralized protocol. Everybody running the protocol is running the same copy of the algorithm, in general. And so even if, say, Chase Bank, JP Morgan Chase, is creating their own blockchain, if their code is publicly available and I can, oh, sorry, I have some noise in the background. Give me one sec. Sorry about that. So yeah, I can publicly verify all of the properties of the protocol myself and assess it for what it is. This is leaps and bounds better than what we have right now, which is JP Morgan Chase using its own proprietary software and not letting us know what software they're using. So to make a long story short, I don't think it defeats the purpose of decentralization, because at the end of the day, a blockchain being run by a big bank is not owned by the big bank. The big bank is just one node in the network. And so it's still a big step forward. And I think it's probably a good step forward in terms of blockchain adoption in the real world, because these are the entities that, big banks are the entities that have the most to lose when it comes with blockchain adoption. And so giving them some skin in the game for it to succeed, I think, is ultimately going to be a good thing. What else do we have? What kind of features need to be in a blockchain to allow people to make zero-knowledge proofs? So this is one of the cool things. The blockchain and the zero-knowledge proof are actually totally perpendicular or orthogonal tools. So any blockchain that you have allows you to post data to the blockchain. And that's actually all you need, because what you do is, instead of posting the data that you would have posted, you just post commitments to the data and zero-knowledge proofs about those commitments. And so you actually don't need any additional features on a blockchain other than the ability to store data, which is the central feature of any blockchain. Is the process to obtain off-chain data an interactive process, i.e., owner of original data must give consent, or does this vary from system to system? That's a really good question. So I believe you can do it either way. There is a way to sort of non-interactively give permission to the data. So I assume when you're saying off-chain data, what you mean is some piece of data that's private that I've committed myself to on the chain, but that isn't actually available on the chain. And so the answer to that is it depends. I can either sort of give out a special key that somebody can just use on the commitment to sort of invert it and get back the original piece of data, or I can require that it be a more interactive process and that they actually request the original data from me, in which case it's even easier, right? I can just reveal the data to them. I don't have to go through the process of making a special secret key. And we've got one more question. Why not use databases rather than blockchains? Is it worth the cost and transition to this new field? After all, security has been compromised in several blockchain projects too. This is a great question. So, I mean, the main answer to this question is the centralization point that I brought up earlier and all of the possible abuses that can happen on a centralized database. So it limits your control over your data, your agency, it limits your protection from outside threats. But, I think your question gets at something a little bit different, which is, how do we deal with the fact that all of this new and emerging technology is going to be flawed at first? Because that's always the case. Whenever there's an emerging technology, the first emergers in the field have flaws, and people have to assess exactly what you're saying. Is it worth the cost to transition? So in my opinion, it is worth the cost of transition. In the end, once a blockchain software is at the level of reliability that traditional software is at, then people are going to wonder why you would ever use anything else. So, it's worth thinking about a little bit of history and how far our own traditional software has come in terms of security and how long it's taken us to get there. And to understand that all software is going to have bugs in it at first, but there is going to come a time when blockchain software has been made and remade so many times that there are so many good standards that you're going to be able to trust it in the same way you would trust a traditional piece of software, except more, because you don't just have to trust the software right now, you have to trust the person operating the software. And blockchain software, what it gives us is a way to no longer trust the person operating the software, because the person operating the software is us. And with that, I think we will move on to the next section. So just to sort of recontextualize ourselves, we learned about the basics of zero-knowledge proofs, what they do, how we use them in blockchains. And now we're going to, basically make you guys experts. So what we're going to do is we're going to talk about, if I'm given a zero-knowledge proof system, how can I measure how good it is? What do the different kinds of zero-knowledge proof systems look like? And where's the current state of the research today? So how do we measure the quality of a zero-knowledge proof system? The most basic way to measure is to look at the communication complexity, which, some of you might know, is just to look at the overall communication in number of bits. So between the prover and the verifier, how many bits have to be sent back and forth in order to both prove the statement and to verify the statement. You can also break this down into looking at how many rounds the communication takes. And we've already seen a little bit of this when we measured zero-knowledge proof systems on whether they were interactive or non-interactive. So that's to say, are there 2 or more rounds of communication, or is there just 1 round of communication? Now we can also measure the system in terms of how hard the verifier has to work. How much time and space does it take on the verifier's machine to verify the validity of a proof? Or we can make the same statement about the prover. How much time and space does it take on the prover's machine to actually generate the proof? And one of the more interesting and nuanced points, we want to look at whether the zero-knowledge proof system requires a trusted setup. And this might not make sense now, but we're going to go into a little bit more detail on what this means. So what is a trusted setup? The basic idea is that a lot of protocols can be a lot simpler if players begin with some kind of correlated random values. So we've already actually seen an example of this in our encrypted messaging protocol from earlier, where Alice and Bob can have this very snappy and efficient and simple encryption scheme, but it requires that they agree upon this value k in advance. So these 2 values k are correlated, in this case, in the sense that they're the same number. But more generally, Alice could hold k and Bob could hold k plus 2, or Alice could hold k and Bob could hold 2 times k. Depending on the protocol, a different correlation between the values that different people have might be more useful. Now, there are some problems with It's set up like this. So the main problem that we're going to talk about is the fact that the person that produces this randomness, if it's not Alice or Bob themselves, has to throw it away, because anybody else who knows this random value is just as powerful as Alice and Bob in the protocol. So there's no security guarantees. Going back to the encrypted messaging example, they could read any of the messages. There's no guarantee that somebody listening who holds the secret value K, they're going to learn everything in the protocol. Now, this is particularly bad when you think about using zero-knowledge proofs for finance, because if I am able to break the security guarantees of a zero-knowledge proof system, then I'm able to prove anything that I want. So I could prove that you transferred me $100 million, and nobody would be able to detect that. And so not only would that be bad for you, but it would be bad for the economy, because if I just say I created $100 million out of thin air and prove the validity of that, then the whole economy is going to bust, because there's going to be tons of inflation and nobody's even going to know it's happening. Now, to get around this problem, we can actually sort of hedge our risk by, instead of trusting one person to generate these random values, we can get a bunch of people to try to generate them together in a kind of trusted setup ceremony. In this case, only one of however many people you get would need to throw away their random values in order to maintain the security of the system. But this still incurs some risk. If nobody discards their randomness, then you have no security guarantees again. And the protocol to do this is a lot more expensive. So you're incurring a lot of expense and you still have a lot of risk. So it's not really the best solution. And just to illustrate what I just mentioned, kind of what I already said, if Eve was the one trusted to generate this random value, which I now call R, then when Alice tries to send the ciphertext over to Bob, Eve can just grab that ciphertext herself, subtract the random value R, and learn Alice's message. So this is super bad, and we've lost all of the keys of our encryption scheme. So that is trusted setup and why trusted setup is. So with that in mind, let's jump back a little bit and describe what are we looking for in terms of an ideal zero-knowledge proof system. So like we already mentioned, non-interactive zero-knowledge proof systems in the blockchain space are super useful because we can broadcast what we're proving onto the blockchain and anybody can verify it. So the ideal zero-knowledge proof system for blockchain and more generally is always non-interactive. So you can think another reason why you would want non-interactivity more generally is just because there's network latency. And so if I'm proving something in zero knowledge and I have to talk back and forth with you over 5 rounds, then I get 5 times whatever the network delay is added to the runtime. Whereas if there's only 1 round of communication, I only have to deal with the network delay once. Sort of in the same line, we want our proofs to be short so that communicating them doesn't take very long and it doesn't take very much bandwidth. We want our prover and verifier to not have to use too much time and space in order to prove and verify statements. And for all the reasons we just mentioned, we don't want a trusted setup. And that's basically it. So now we know how to evaluate a zero-knowledge proof system. We look at it, we say how many rounds of communication are there, what's the overall communication complexity, how fast is the prover, how fast is the verifier, is there a trusted setup, and we can compare them. So next we're going to take a look at an extremely recent result, which, this came out like last week, so you guys are getting cutting edge information, and we're going to kind of evaluate according to the metrics that we just said. But before we do that, I'm going to pause and take any more questions that we might have gotten. So it looks, unfortunately, the Q&A questions are sorted by votes, so I kind of have to pick through and see which ones are new. But I think we only have 2 new questions. So one, how is it verified that the commitment made is to a legitimate value? So this is precisely the point. So that's what the zero knowledge proof does. So the zero knowledge proof proves that exact statement. The value that I committed to is valid. And so you take that statement, you deconstruct it mathematically, you prove it in zero knowledge, and then whoever wants to make sure that you didn't lie and commit to having a balance of $1 billion, they just go on there and they check the zero knowledge proof. And mathematically, you are guaranteed that if that proof checks out as valid, there's like a 99.99999% chance that what you posted was actually a valid transaction, even though the rest of the committed value is totally hidden. And one more question, can we apply zero knowledge proofs to Bitcoin? Yes, actually. So people have done this. They've built zero knowledge layers on top of Bitcoin. So, you know, a lot of people like to talk about layers when they talk about blockchain protocols. So zero knowledge proofs are not a layer 1 feature in Bitcoin, but you can apply them in layer 2, which basically means you can create an application on top of the Bitcoin network that does use zero knowledge proofs. And it basically exactly what I told you. You, instead of posting an actual transaction, you just post, you know, a commitment to the transaction and a proof about that transaction. But it's very inefficient because it's not native to Bitcoin. So you're much better off using some kind of, you know, Zcash or other privacy-focused blockchain solution. All right, so if there's no other questions, let's talk about QUARKS. So the new paper that was released last week is called QUARKS, and it stands for Quadruple Efficient Transparent Snarks. So let's start with the basis of that statement. What's a snark? Because that's already a new word. A snark is an acronym, and it's a succinct, non-interactive argument of knowledge. So the word succinct here means that the length of your proof is, in some sense, less than the statement that you're proving. So if you take the statement that you're proving, you know, I want to prove that X is valid, and saying X is valid uses this circuit, these rules, then the length of my proof is actually less than the size of the circuit. And so, you know, this is a really wacky property which says that verifying a zero knowledge proof actually takes less work than it would take to verify the non-zero knowledge version of that proof. You know, if I just wanted to verify the statement without any kind of zero knowledge property, you would give me the statement and I would plug it into the validity circuit. And so I would go gate by gate and I would evaluate it. And so this succinctness property is really, 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 really cool in that it's saying that with zero knowledge, you can actually get something that's even better than zero knowledge, or, you know, totally different from zero knowledge. What you can get is a proof that takes less work to verify than it would take to verify it in a trivial way. And so this is not only what I mean to say is that this succinctness property means that zero knowledge proofs, or snarks, not only improve the privacy of a blockchain, but they actually improve the efficiency of the blockchain. They improve, you know, how powerful you have to be to verify these statements. So the second term is non-interactive. So we've already gone over this. It means that there's only one round of communication. And the last phrase, argument of knowledge, isn't too important, but basically what it means is that the statement you're proving is like, I know some X. You know, I know some X that produces this commitment, and so that's an argument of knowledge. If you were proving some other statement that didn't have to do with knowing something, then you don't need an argument of knowledge. But this is a nitpick detail. And so if you think about this for a little bit, you'll realize that these, two of these properties, the succinct and the non-interactive, are already, two of the ideal properties that we were looking for in our ideal zero-knowledge proof system. So we want short proofs, we want low communication, we want few rounds of communication. And so all we have left is to get an efficient prover and verifier and get rid of the trusted setup. So we would like a transparent snark, one with no trusted setup that has an efficient prover and an efficient verifier. And that would be our ideal zero-knowledge proof system. Okay, so let's talk about QUARKS. What are QUARKS? So QUARKS, is actually two new zero-knowledge proof systems. Both of these systems were developed by Microsoft Research. I'm blanking on the actual researcher right now. I should drop their name though. It's Rinath Sethi and Jonathan Lee out of Microsoft. And it stands for quadruple efficient transparent snarks. And so the efficiency that they're talking about is they have a logarithmic proof size. So when I say logarithmic here, what I mean is you look at the size of the proof, and then you look at the size of the validity circuit, like I was mentioning before. And the relationship is that the proof is the logarithm, the proof size is the logarithm of the size of the circuit. And similarly, the computation that you need to verify a proof is logarithmic in terms of the size of the circuit. And this is really where they've improved upon previous iterations. It's got linear prover computation. So the work for the prover to create the proof is about the same as the size of the validity circuit. So like one operation per gate in the validity circuit. And the crucial property is that it has no trusted setup. Now, when I say trusted setup, this is in the sense that I was talking about before, where you're trusting somebody to distribute these random numbers. It does involve a sort of pre-processing stage. A lot of these zero-knowledge proof systems have a pre-processing stage, but it's not distributing random values that can later be used to break the security of the protocol. Now, let's talk about, what's actually changed here. So there's a new zero-knowledge proof system. So what's different? Well, basically, they've been able to reduce the proof size 3 to 4 times smaller than the previous system. So I don't quite remember off the top of my head, but I believe it's down to like 7 here. I can look at it. Yeah, the previous best was 131 kilobytes for the proof, and now they've gotten it down to 39 kilobytes. So that's an extremely small proof. And they've also been able to reduce the time in this pre-processing stage. So the previous best zero-knowledge proof system had to spend like 20 seconds or so doing this pre-processing. And they've gotten it down to like, 1.6 or 1.8 seconds. So this is, a lot of numbers to basically say we can have privacy and scalability better than ever without relying on some kind of risky trusted setup ceremony. And in the blockchain space, this is particularly important because if you rely on something like a trusted setup, then people are going to be able to arbitrarily deviate from the protocol if they get their hands on these random values. So basically, we've been able to achieve highly efficient zero-knowledge proof system for applications in the blockchain space. And more or less, it's the closest to ideal zero-knowledge proof system that we have, and the latest and greatest stepping stone on the path towards some kind of perfect zero-knowledge proof system. And that's all I have. So thank you all so much for your attention and for inviting me here to talk about this. This concludes the presentation, and I'm happy to spend the rest of the time taking any of your guys' questions. So I'll pause for maybe 30 seconds to a minute, and feel free to post any and all questions in the Q&A.
Well, that looks like we're good. Looks like there's no more questions.
Okay, awesome.
Well, Eli, thank you so much. Really, really appreciate your time taking it out of your Friday night. It's Friday night here on the West Coast. Yeah, Lai Wen, do you have any concluding remarks? And I believe you're muted, by the way.
Oh, sorry. Yeah. Thanks for taking your time out to educate us on zero knowledge proofs. I think it supplements our own education over at the FinTech Society very well, and I'm sure they're very grateful for you as well. Yeah.
Yeah, the applications for zero knowledge proofs and decentralized finance, particularly, I think, are absolutely fascinating. Particularly, being able to take these things that traditionally are, sort of siloed within traditional finance, like credit scores per se, and bringing them into a sort of more open, permissionless industry and ecosystem where, for those who are familiar with like decentralized lending and borrowing, you have to over collateralize your loans, which means you have to put more money in order to take any money out. So I have to put down $11 to take out $10. This is really only useful for traders trying to make money. But if you were able to bring over some sort of like legitimized, credit score or way to assess risk from, the rest of the world, how we get our loans, now we're able to transact in this like absolutely new way in the new permissionless ecosystem. So I think the applications are sort of endless, and I'm actually looking sort of towards the audience to figure out, it's up to you to like make this reality. Like there's open source libraries, there's, these are out there. It's still very early, so if you learn about this stuff now, you will have a lot of, I guess, advantage in the job space. Even people like at blockchain companies, I talk to them all the time, still don't know what zero knowledge proofs are, and like still don't know. So this is like the most cutting edge. And the fact that we have Eli coming and talking about QUARKS, these things came out last week. Like these things take years for sometimes to be like applied. So it's really cool that Eli was able to come and do this. And Eli, I think you got one more question. Are QUARKS open source?
Dig through the paper right now to try to figure that out, because that's a great question. So what I'll do is I'll post a link to the paper right here. This is what I've seen so far. And I don't think, oops. Here, I posted it in the Q&A, but by accident, but I'll post it in the chat. What I'll say is, since it's from Microsoft, I kind of doubt that it's open source, but they definitely do have an implementation running because they have experimental results in their papers. So it's possible, and then I just haven't found it yet. So go ahead and dig for yourself, and if you find it, I would love to hear about it.
Yeah, it's like there's one thing about being an open source, and then there's another thing about like having a job like API to play with it, like actually being able to like use it. So I doubt that that's the case, unless it's there. That is the case. I'd just be surprised.
Yeah, there's a general trend in cryptography where academic works will open source their code because they have no financial incentive not to, and places like Microsoft and Google generally will not. So if that's the case, then I wouldn't expect it, but there's always a chance.
Makes sense. So we're going to hop into networking now. Everyone's more than welcome to stay. Eli, I do have a couple questions for you regarding, I know you probably want to get out of here soon just because it's getting late here on the West Coast, but just around the idea of like innovation happening in academia versus industry. And like, this is a paper that's coming out of a, company, but a lot of these concepts have been, researched for decades. So where we're seeing the next sort of revolution in cryptography, whether it's going to be in academia or industry, I'd love to know. But can we hop into networking for that? Because I would like to hear other people's opinions.
Yeah, let's do it.
So everyone turn on your mics and cameras. There's going to be these virtual tables. We'll be able to like hop from table to table. Feel free to hop around. If you enter a new room and somebody's talking, just wait for them to finish talking or have you to introduce yourselves, just for some networking 101 in the virtual world. It's kind of a weird thing. But yeah, we're going to hop into networking and stick around. See you guys. Thanks again, Eli.
Yeah.